Now, today, though, we've got the second half of the last chapter, and it's my great pleasure to welcome my friend and colleague Brent Edwards to talk about this. Now, Brent got a year in CS at the University of Minnesota and stayed on there and got a PhD in signal processing and auditory perception. Now, then he moved to the West, into the Bay Area, San Francisco, and joined Resound, now GN Resound, a Bay Area hearing aid company. He was in Resound for quite a few years before jumping out and becoming involved in a startup called Sound ID, which was a PSAP, a personal sound amplification product. Intended initially as an over-the-counter hearing aid, but became a Bluetooth headset with hearing aid functionality. He then moved on to Starkey Hearing Technologies, and this is when I met Brent. He was Vice President of Research. He was there for more than 10 years, lived in San Francisco, but the research center was in Berkeley, and then moved on to another Bay Area startup, although a fairly mature startup, Earlens, where he was CTO. After an extensive period of his life in the Bay Area, he jumped the Pacific and moved to Sydney, Australia, and is now director of the National Acoustics Laboratory, which I'm sure is known to all of you, where he's been there for more than 6 years. So, Brent, I can't think of anyone more suitable to be talking about hearing aids and cochlear implants. So let me shut up and give you the floor.
Great, thanks, Simon. And it's I really appreciate the opportunity to speak on this topic. And I'll just start by saying, you know, I used to write and talk a lot about compression and auditory modeling and their relationship to hearing aid design. So basically what I've done is I've gone back and I've stolen a lot of slides and figures from various papers and publications in my earlier career, because what I want to talk about is sort of the evolution of how hearing aids, signal processing, particularly compression, evolved and was informed by auditory models, and also how to think about the use of auditory models in the assessment of how well hearing aids are doing their job. And I'll also say, I'm not going to talk about cochlear implants. It's kind of outside of my field, and even though I know what they do, I thought my time would be better spent focusing on hearing aids, and CIs would be a whole other lecture. Maybe we can have our Cochlear Corporation colleague, Zach Smith, talk at some point about that. So anyways, evolution and evaluation of auditory model-driven hearing aid design. And again, back in the early days, when thinking about hearing aids as they were transitioning out of linear transistors, linear gain transistors, the more sophisticated designs were driven by models such as the CARFAC, and were driven by psychoacoustics, which auditory models have been in many ways built to produce the same output as auditory models. So there's almost like a virtuous circle here between hearing aid design, psychoacoustics, physiology, auditory models, where they're all informing each other and they're all interrelated. So I think I'll give you a sense for that in this discussion. So, and feel free to jump in whenever you want. The only person I can see on my screen is Simon, so I can't see raised hands. Just feel free to shout out.
So, Brent, is there something you can do to reshape your screen? It's kind of letterboxed in both dimensions, so it's not as big as we'd like. It's maybe.
Yeah, it's because I've got a super wide screen here. Let me try to see if I can share a different
share a window instead
different
of
way of whoops, that didn't work. Different way of sharing what I have. Good. What I might do is switch I'll switch the presentation to my laptop, which doesn't have a wide screen. And swap displays. There we go. And now share. Boom. How's that?
Much better.
Okay, cool. So there's actually quite a lot of uses of auditory models like the CARFAC in the hearing aid world. And so some of them, the most obvious one is informing signal processing design. And if you look at everything that exists in a hearing aid today, and there are, probably a couple dozen signal processing features in there, it's really only one, to my mind, multi-band compression that has been driven by auditory models and is, really being informed by auditory models and compared to it. Everything else is kind of driven by other purposes. And I'm curious if anyone else has a different perspective on that. But noise reduction, directionality, beamforming, frequency lowering, all these kind of things are driven by our understanding of auditory perception, which of course are driven by our understanding of auditory models, but not directly so. Gain prescriptions, which is taking someone's hearing thresholds or audiogram and figuring out how much gain and compression to provide within a hearing aid, also rely quite a bit on auditory models. So the NAL-NL2 prescription, which is the most widely used in the world, has an auditory model in there. And people have used auditory nerve models similar to the CARFAC to, well, when I say auditory nerve models, models that produce auditory nerve responses at its output in order to derive gain prescriptions as well, using something similar to what the hyperpersonalization project is doing, which is trying to minimize some error signal, at the auditory nerve level. Auditory models are also quite extensively used in the prediction of sound quality with hearing aids. So the Hasky by Jim Cates, for example, is one of them. And they're used to understand what the perceptual consequences are of noise reduction, distortion, and so on, to try to get an objective metric of quality without the need for human involvement. And here's an example of from a paper that Jim recently published that summarizes some of his work. And this schematic of the cochlear model should look, have similar components to what you've been seeing and discussing throughout the Dick's book. Finally, also, auditory models are used so that we can understand what is the consequence of hearing loss on general auditory function. So if you make changes to the functionality of the inner hair cell or the outer hair cell, you can then see what the impact is on the signal that is, the way that the acoustic signal is then encoded at the auditory nerve level. And some of its uses has been used to model psychoacoustic measures of hearing loss. So psychoacoustic differences between normal response and the response of people with hearing loss, and also the failure of the articulation index and other measures to predict the performance of people with hearing loss. So the AI or the SII does not do a perfect job of predicting speech intelligibility like it does for with hearing impaired people, like it does for normal hearing. Auditory models have helped to inform why that might be. So generally speaking, in the field of hearing aid design, development, and investigation, these are where models like the CARFAC have found their use. I'm really going to focus on that first one, which is signal processing design, because that was a big part of how I used auditory models and thinking about what we should be doing with hearing aids. Now, just for a quick primer for those of you who maybe need a reminder about hearing loss, this is where a schematic of pure tone thresholds in the solid line for people with normal hearing, and in the dashed line, what the pure tone threshold might be for someone with hearing loss. I plotted this on dB/SPL in the y-axis, that's frequency on the x-axis, and SPL is how most of us probably think of sound, but unfortunately in the hearing aid world, we flip that upside down and we plot things in terms of dB hearing loss. So the further down you go, the more of the difference. It's a plot of the difference between thresholds of the individual and the threshold of normal hearing. So a measure of 20 dB at a certain frequency here means you're 20 dB worse than normal. So that's why it's kind of flipped upside down. Down is worse. Now, this figure has been quite, this measure of basal membrane mechanics has been quite important in understanding hearing loss and the design of hearing aids. What it shows the basal membrane velocity or response at a given frequency in a healthy cochlea, and then in an impaired cochlea. And you see that what you can see here is there's quite a large loss of sensitivity at low levels of sounds, but very small losses to sensitivity at high levels of sounds. So this means that there's a level dependency here, a nonlinearity in the impact of hearing loss that is then going to inform hearing loss design. And of course, if you look at cochlear models like the CARFAC, you see those nonlinearities embedded in there. And so, we see the mechanics of the nonlinearity, we see the auditory models that are in part informed by measures like this. And then that informs, what's going on in the human and how we might want to design hearing aids because of it. Now, this is a psychoacoustic measure that demonstrates a similar thing. These are loudness growth curves where the person is asked to rate the loudness of a tone or a narrow band of sound at different levels. And here you see the growth curve for someone with normal hearing, the growth curve for someone with hearing loss. And you see the same phenomenon, quite a significant loss of sensitivity at low levels, but not much sensitivity loss at high levels. Again, indicating a nonlinearity going on. And if we just kind of plot the two together, you see that they look quite similar. And there's other psychoacoustic measures comparing normal hearing to hearing impairment, where you see the curves are very similar to the basal membrane response and the curves that you would see in your auditory models in terms of the responses. So again, it's all kind of informing what's going on perceptually with that hearing loss. Now, back in the 80s, when hearing aids were linear, this is the best that we could do in terms of compensating for that change in loudness growth. So it's a linear shift of loudness at all input levels. And you can see what happens is you actually have not enough loudness, or it's not enough gain at low levels, but it's too loud at high input levels. So the gain is too much. So if you just apply linear gain, it's just right at a certain level, but below that, it's going to be not enough gain, and above that, it's going to be high enough gain. But at the time, there was nothing you could do because the technology wasn't able to do compression. So what we have learned from a variety of many publications and research is what is the effect of compression on auditory perception, but also how does it function? And so you'll see that this has informed auditory models that this compression in the auditory system is very fast acting. It is it has band pass characteristics, relatively narrowly tuned, depending on the level. These auditory filters are, overlapping. I think of each inner hair cell as having its own auditory filter. So, 3,500 filters that span, the bandwidth of auditory perception. But when you look at something like this, it can inform how much gain you should be providing in a hearing aid at different levels. So if you just say, how much gain do we need for this input sound in order to produce the same level of loudness for the hearing impaired person, this says you need that much gain for an input of 50 and that much gain for an input of 80. So these kind of understanding the mechanics of auditory function for normal and impaired can then inform you of how to design your hearing aid. And one of the obvious things that comes out of that is level dependent gain. And looking at these differences can tell us how much gain gets applied at different levels. And as I alluded to earlier, the most common gain prescription, LL2, actually looks at something like this to figure out how much gain to provide. And back when I was at Resound and we actually created the first gain prescription for compression hearing aids, this is exactly what we did. We use an auditory model to predict the loudness growth of the hearing impaired person, compared it to normal, and that informed the gain that we would provide at different input levels at different frequencies. So if you take this curve that I've got here, you would then, given that method I talked about, figure out how much gain do you need at different input levels in order to restore loudness function to normal, if you define normal as those two curves. And if you were to use the CARFAC, and with this idea of you're minimizing an error function, at the output of the cochlea, you would come up with a similar kind of curve in terms of normalizing at least probably the total response at the auditory nerve for those with hearing impairment versus normal hearing. So basically what hearing aids did at the time with that understanding is they produced gain curves that look something like this, linear up to a point. Then you had compression where the gain reduced as the level increased, and then you'd go back to linear at some point in the system. And the audiologist who fit the hearing aid to the person with hearing loss would be given control of the gain at a low input level and the gain at a high input level. And this way they could individualize the gain at a certain frequency for that person. So if both gains were the same, of course, it'd be linear at that frequency. They can increase and decrease the compression ratio and adjust the overall gain at that frequency. And this just kind of shows you the equivalent input-output function for the gain curve here on the left. So, and if you apply a gain function like that, this is what you get for that loudness, that impaired loudness function. So again, solid line is a normal loudness function. This dotted line is the loudness function for someone with hearing impairment if they are fit with a linear hearing aid. If you fit a compression hearing aid well to what we predict is the mechanics of the loss compression that you might measure in the CARFAC, then you could restore this loudness function for that person at that frequency to something that's pretty normal. So again, understanding what's going on in the auditory model can tell you how to then compensate at the hearing aid level in order to restore auditory function at the output of the model. So the first multi-band compression hearing aid that was ever produced was by Resound in '89, and it actually came out of Bell Labs. John Allen, who many of you might know, played an important role in the design of that compression. He took his understanding of cochlear mechanics and auditory models and designed a simple two-band compressor and a fitting prescription for how much gain and compression to put in each band based on hearing loss. Now, the reason it's so simplistic with a low-pass filter and a high-pass filter, and each of these filters has their own compression functions, is because this was an analog chip that had to run on 1 milliwatt of power and be small enough to fit in a hearing aid. And it took years and tens of millions of dollars at Bell Lab to just develop that chip so that it had, low noise floor, good fidelity. So back in the day of analog, this was in analog hearing aids, this was very, very difficult to do. And that's why it took until '89 to develop something as simple as this. But what you can see is what you end up with you remember that hearing loss is more in the high frequencies than in the low frequencies. This would be a typical output of the Resound hearing aid at that time that you could do with these, just a 2-channel system. You could have for 50 dB input, the gain starting low and then increasing quite significantly above a certain frequency. But at higher levels, you'd have less gain and you'd have less of an increase in gain. And with this Resound hearing aid, you could adjust the crossover frequency of these two filters. So you could not only adjust the shape of the gain curves here, but you could adjust where it starts to increase in frequency. So that's pretty sophisticated at the time, but obviously pretty simplistic when we think about auditory models and auditory function. So compression evolved more dramatically and started to look more like auditory models, where we started to introduce multi-band compression, where you now had multiple filters within that span the auditory bandwidth, and within each filter you had an AGC, where the AGC was very similar to what an AGC would, do in an auditory model. And then you, of course, synthesize each of the bands back together to produce the output. It's a pretty simplistic version of multiband compression here. Something that's a little bit more realistic of how it was implemented in a digital hearing aid, which typically used overlap add FFT approaches. So you take your frame, you would, have a bunch of filters within that frame, estimate powers. You'd have time constants that would smooth your power estimates, and I'll get to that in a second. Figure out your gain, apply the gain to the signal, and off you go with your inverse FFT. And I think a lot of hearing aids today function relatively similarly. Now, in terms of thinking about how to inform this design from an auditory model, there are several parameters that you can adjust. One is the shape of the filter, and I'll get to that in a second. And also, the time constants, the dynamics of how these systems worked. And I'll get to that as well. But first, the filter shapes. So way early on, when we were looking at very simple 2- and 3-channel compressors, we realized that there was a problem when thinking about filter design theory when you're actually working with nonlinear filters. And that's this. Typically, if you had a 3-band system, you would have your low pass, band pass, high pass filters, and they would overlap at the -6 dB point. So if you wanted a nice flat response, each filter would have the same gain, and you'd have a nice flat gain response given to it. The problem when you introduce nonlinearities like compression into each of these filter responses, it doesn't interact the same way anymore. And what we realized was if we ran a pure tone sweep across this filter band where each was programmed identically, so let's say identically 20 dB gain with 3-to-1 compression, and you ran a pure tone sweep across it, you would see these artifacts, these distortions in the gain near the crossover points, because what's happening is the tone is reducing in level, and because of compression, the gain is increasing the gain at that point. And so now you don't have a nice flat response anymore, even though each band is programmed with the identical gain functions. And you can see it that the problem actually becomes even worse when you start to provide different gains and different compressions in different bands. What you think you're providing based on your intuition with linear theory, the compression is actually giving you more gain than you anticipate. I think I saw a hand go up. Is there a question?
You're muted, Chinwe.
I'm sorry. Yeah, I have a question about the multi-band compression. So it's done in frequency domain or in time domain?
You can do it in both, but typically it's done in the frequency domain these days. In fact, all hearing aids, I think, do it in the frequency domain in some way.
Is there any pros and cons between both approaches?
Yeah. Latency is the biggest one. So in the time domain, the difference, the time delay of the system introduced by the processing can be sub 1 millisecond. But when you use FFTs, you're restricted by the window size that you have. And so now you have multiple milliseconds in throughput delay, and that has some perceptual consequences. But there are advantages of being able to capture a frame of data in terms of noise reduction and other signal processing features. But there's a big argument that some people really love analog hearing aids because of that, microsecond delay in the audio, and they're worried that comb filtering and things like that has a perceptual consequence on the summation of the amplified sound with the unamplified sound coming through the ear canal.
So all of those filters, for example, you have 3 filters there, so in frequency domain or in time domain?
So it depending on your design, I mean, in the frequency domain after an FFT, you would have your analysis synthesis, you would have your analysis filters in the digital domain, defined across basically the FFT to produce your power estimates within the band, which then you apply your gain as a function of level, your compression, and then you resynthesize the bands back together.
Thank
you. Another question?
Yeah, the the issue that you're depicting on this slide here is really a pure tone phenomenon, right? If you were using a broadband signal, you wouldn't see quite as dramatic an impact of the band edges as you do in this, because sinusoids are kind of a pathological signal for exciting, in a limited way when you get to the band edge, right?
What kind of stupid question is that? I'm sorry, Kelly Fitz. I think I recognize your voice.
Yeah, I'm not in this. I'm not in this industry. I'm kind of a rookie here.
Good to hear you, Kelly. Good to see you too now.
Yeah,
in fact, if you read this paper in '98, what we described the red curves as, that's a response to a broadband sound.
The red curves is the response to a broadband sound, and the blue is the response to pure tone.
Pure tone sweep. So it starts to get at the differences between, you in a linear system, you don't think of any differences, but if you have broadband sounds that have the same power in each band as pure tone does, you actually get a different response. Mm-hmm. So what you said is absolutely right.
Thanks.
So our solution to this back in the day. Oh, another question from Greg.
Yeah, thanks very much. Having listened to that answer, are we actually interested in pure tone responses? What do they reflect in the real world?
Music? Maybe?
Yeah, but even not really, I guess.
Yeah, so, that's a great point. Back in the day, we argued exactly over that, and I probably was in your camp, sort of like a who cares. But from a theoretical perspective, we thought we could come up with a solution that was a little bit more signal agnostic from that perspective. And there's psychoacoustic reasons why this is a problem, and that's primarily loudness summation, where perceptually the loudness depends on the bandwidth of a sound, and this design will cause problems.
Yep. Okay. Thanks very much.
Yep. Another hand?
Look, if you want to keep going, I can save it till later, but it's yeah. Do you want to keep going, or shall I save that question till
happy
later?
to.
Okay,
happy to hear.
Great. So I guess thinking about the different contexts in which we are hearing and listening to things, the information that we are interested in can exist in different parts of the frequency spectrum. And this has got me thinking about whether in the development of hearing aids, it's possible to explore and pay attention to how people can direct their attention to different aspects of a sound signal. I recognize that, with a multi-dimensional stimulus and a multi-dimensional transformation going into a multi-dimensional sensing device like in here, you very quickly run out of the ability to adequately explore the dimensions of that space. But in evaluating these hearing aids and developing new ones, is consideration given to the way that people might direct their attention to different parts of the frequency spectrum?
Yeah, absolutely. And the way that I think I thought about it, in large part due to some of the discussions at Karma at Stanford with Malcolm Slaney, and that's, if you think about auditory scene analysis and the cues that are important to form auditory objects, common modulations, common onsets, common harmonics, common ITD, ILD, that kind of thing. It's important that the hearing aid preserves those cues and doesn't distort them, keeping in mind that the auditory system is, in fact, distorting them. So you kind of want to bring each of those cues back to normal. And I talk a little bit I've got some slides that demonstrate that a little bit later on, but I do think about it holistically as how are objects represented in a normal hearing system? How are those representations distorted because of hearing loss? and how can your hearing aid processing bring those cues back to their saliency?
Wonderful, thank you.
Yeah, thank you. So our solution back then was basically to have heavily overlapping bands. And so you can see here, it's not your classic bandpass structure where you just have them crossing over at, the 6 dB point. But you've got, at any given frequency, you have multiple filters responding at that frequency. And if you think about it, this is exactly how the auditory system works. It's exactly how the Carfax model works, is you have, the difference in the center frequency of each filter is quite small. And so when you design it that way, and then you look at this difference, as Kelly rightly pointed out, the difference between broadband response and pure tone response, then you start to see not much of a difference between them at all. And so that helped out a lot. Now, Eric Lindemann, who was at Audiologic at the time, mathematically analyzed this as an oversampling problem in the frequency domain, and that these artifacts were kind of like aliasing, but I won't get into that. So this is the filter band that we introduced in 1999. You can't really see them, but there are 14 filters there that are highly overlapping. And there are multiple benefits of having this overlapping structure from a psychoacoustic perspective, which again, I think for everyone in the audience would say, well, of course, that makes perfect sense. That's what the healthy cochlea does. But at the time it was novel and it's computationally expensive. So this was not an easy decision to do, but I think from a perceptual perspective, it was the right thing. And if you look at the impact of lost compression on auditory perception, there are quite a lot of different problems that get caused by it. And it's not just audibility, it's not just levels and loudness. It actually has an impact on frequency resolution, temporal resolution, masking effects, envelope coding, everything that I think is important for auditory perception in the real world, again, from an auditory scene perspective. So if you are distorting and making these things worse, which we know from psychoacoustic measures, all of these are worse in people with hearing loss, then you want your processing in some way to help improve them. Now, there is some tension at the time because people thought that compression also made these cues worse, that compression reduced the temporal dynamics, so it would make temporal resolution worse. Multiband compression reduced the frequency dynamics and the frequency variation, and therefore was making frequency resolution worse. So there was some arguments that compression was the wrong thing to do because it was exacerbating these problems that already existed. I think I'm going to try to show you that that was the wrong way to think about things. And compression, if designed correctly, can actually restore these functions that are being caused by the loss of compression in a damaged auditory system. So if you consider the envelope, for example, this idea, it's commonly thought that envelope fluctuations are, the saliency is reduced by compression, and therefore envelopes are not perceived as well when used in compression hearing aids. But if you look at an auditory system, a healthy auditory system, the healthy cochlea is automatically compressing envelopes anyways. And in the Carfax, if you looked at the envelope representation at the output of the cochlea, you would see exactly that and measure the AM, the response to an AM signal at the auditory nerve level out of Carfax. You would get a certain modulation depth at the output. And then if you applied your hearing impairment model in Carfax, you would see an enhancement of the modulation because the cochlea has lost its compression. So in fact, putting compression in a hearing aid is simply compensating for the fact that the damaged auditory system is not compressing the signal like a normal system does. And if you match the amount of compression in the hearing aid to compensate for the lost compression in the cochlea, you should end up perceptually with about the same perceived envelope fluctuation as someone with normal hearing does. And there are experiments that have been done to show exactly this. And again, things that have been shown perceptually I think now that we have the Carfax model that can be tuned to different types of hearing loss, you can create objective measures at the output of the Carfax model to come to the same understanding of what is the impact of hearing loss, say, on AM. And if you design a new hearing aid compensation system, is that hearing aid compensation system normalizing AM at the auditory nerve level?
Brent,
So
the
yeah.
complexity of that argument is all about time constants, right? Because if you're
thank you for leading me to my next slide.
That's where you're going.
So, yes. So now remember that another important aspect of the design is the time constants that are applied to your estimation of gain. And there's a wide variety of thought in the hearing aid field on what time constants should be. If you took a purely auditory model perspective, you would argue they should be as fast as humanly possible because that's what the cochlea does. It's near instantaneous at the hair cell level. But you have hearing aids that will take seconds to adjust the gain in the real world. And you've got some hearing aids that take milliseconds to adjust the gain. So even today, there's quite a lot of differences in how the dynamics of hearing of the compression is applied. Now, one of the early considerations of the time constants were the artifacts that got introduced in the envelope. So if you have an input that goes suddenly from a low level to a high level back to a low level, typically we talk about attack times and release times. The attack time being how quickly the gain adjusts when the level goes up. Release time is how quickly the gain goes, attack time, how quickly the gain goes down when the level goes up. Release time, how quickly the gain goes up when the level goes down. So we want a very fast attack time in order to ensure comfort that people aren't exposed to really radically loud sounds. If someone's at a low level with 40 dB of gain and suddenly the level goes to 100, you don't want 140 dB coming out of that hearing aid. So you want to turn the gain down very quickly, but you end up with this overshoot artifact that can sound like a click. Conversely, in the release time, when the level goes back down, you want the gain to come back up. But if you don't get the time constant right, here you can see it comes back up in about 50 milliseconds or so. If you don't get it right, you can actually hear what's called pumping in the sound, and you can actually hear the AGC. And the problem with trying to make the release time instantaneous is you get horrible intermodulation distortion in your signal. So it's this balance between the fact that a multiband compressor is ultimately not a very good representation of what's happening in the cochlea. So, when we try to simulate everything like the cochlea does, we end up doing some horrible things if we with the sound quality. So we have to pull back and make some compromises. So the compromises here is in the time constants and the release time. Now this has some consequences on what it does to sound. So again, consider envelope modulation. You've got a signal, input signal with the envelope going sort of up and down. And you've got these input-output functions for normal hearing and hearing impaired. Here's the normal compression. Here's some reduced compression in the impaired ear. At the perceptual level, the loudness is fluctuating much less in a normal ear than it is in an impaired ear. So obviously, as I said earlier, the solution is you compress the envelope so that the loudness fluctuation for the hearing aid wearer is the same as the loudness fluctuation for the normal hearing person. The time constants cause a problem with that. So because you actually have time constants, you have a dependency on how much it's compressing with the frequency of the fluctuations or the modulation. So here, what I did is I just took a signal with a certain amount of modulation depth and looked at how much what the modulation depth was post compression. And you can, these different curves are for different modulation frequencies. And you can see the effect of the compression is modulation frequency dependent. This is not ideal at all and can probably produce some interesting perceptual distortions when you have multiple modulation frequencies going on. But the nature of the design causes that because we can't have instantaneous compression that applies the same compressive effect independent of modulation frequency. I think I saw a hand go up.
two hands up. Shinwei, you're
Okay.
first. I'll have a question.
Yeah, I still have a question about the multi-band compression in the frequency domain. So I see you have a diagram to show you do FFT and then you apply filtering on each of them. I'm assuming the filter is the IR filter, right? It's not the like FR filter. So
well, in the frequency domain, you just specify at each of your frequency bins what the attenuation of that filter is. In the time domain, it would be, you know, FIR. Yeah.
So is there any issue when you do this kind of multi-band compression in frequency domain? Is there any discontinuation issue when you revert back to the time domain?
You can have some aliasing, introduce aliasing if your gain as a function of frequency changes too much. So when you do your inverse FFT, you can have aliasing in the time domain that gets so what we do is again, the practical implementation is you would then filter the gain function so it doesn't change so much, like low pass filter the gain function as a function of frequency now, so you don't have such dramatic gain changes as a function of frequency to prevent that aliasing. Now, in the FFT, within each band, it's got its independent gain level estimator, and it's that level estimator that has a memory and has a time constant to it. But two time constants, one depending on if the level's going up, another if the level's going down. That produces the effect you see on the screen here.
So I'm sorry, I still have one more question. So in terms of computational cost, to do that in time domain or to do that in frequency domain, I think there's no advantage of doing that in frequency domain, right?
There is, because of all the other frequency, all of the other signal processing that you can do. So noise, for example, in that old hearing aid, we did noise reduction at the same time in the frequency domain. And it just made it computationally, we could do that. We couldn't do that with a time domain implementation, given the low latency we needed and the low power.
Thanks.
Yep.
Greg.
Yeah. So thanks very much, Brent. Really nice and simple description of how the compression function restores the amplitude modulation depth. But of course, the person at the end of the hearing instrument doesn't have hearing that worked like everybody else's hearing. Have you got some thoughts on whether restoring the original modulation depth is actually the right thing to do in terms of perception?
So it's a great question, and guess I'll say is if you have that loudness growth function for that individual, you can probably take a pretty good shot at restoring envelope perception. The problem is, you know, some of the damage is inner hair cell, some of the damage is outer hair cell. There might be something going on at the auditory nerve as well. So it's not just compensating for lost outer hair cell gain that's going on. And that's when you get to that complexity. And who knows centrally, upstream, what adaptation has occurred due to, you know, poor loss sensitivity for many, many years. You know, if central gain has increased, you know, all bets are off in terms of trying to restore these things back to normal.
Yeah, so it's a hard problem. Okay, so
thanks.
Yeah.
So what I published many years ago, I don't mention it here, but something called the psychoacoustic Turing test, which is if you've got a subject in a sound booth and you give them a whole bunch of auditory tests, if they look normal on every single auditory test that you give them, according to what your norms are, the hearing aid has done its job in producing a normal hearing person. If you can't give a test that produces abnormal results. So and of course that's based on the idea of Alan Turing's Turing test. If someone on the other end is responding to you in a way that you can't tell if it's artificial or not, it's passed the test. So this is sort of a cyber hearing Turing test. And that's driven a lot of my thinking about hearing aid design, that is trying to restore all of these basic auditory functions to some norm. And in the CARFAC, what the way you would think about it is you'd look at the output of some measure with a normal functioning auditory system in the CARFAC, look at the, say, the auditory nerve response, and what can you do at the front end with an impaired model in the CARFAC to produce a very similar output.
Yeah. Okay, thanks very much.
Yeah, thanks, Greg. So one example of what I just discussed is considering forward masking. And forward masking is considered a measure of temporal resolution. Now, I see a hand has gone up again.
Greg's is still up, but that's okay.
Okay. So forward masking is measured where you have a long-term masker, then you have a brief, millisecond pause, and then you have a very short signal at that frequency. And you measure your detection threshold of the signal as a function of time interval between the masker and the signal. So here's sort of the classic data that you expect to see here with normal hearing. As you start to temporally separate the masker from the probe, the threshold at which you can detect the probe drops quite quickly. And so that's a measure of the temporal resolving ability of the auditory system. Now, if you do that measure with someone with hearing loss, this is a pretty typical measure. And this is interpreted as the impaired auditory system has very poor temporal resolution. So how are you going to solve that? Impossible. You can't change timing in someone's auditory system. But again, I think if you apply the auditory model to this, then you get a different interpretation. So what you can do with these curves is calculate a gain function as a function of level. So say for 40 dB input sound, you need about 30 dB of gain in order for a 40 dB probe signal to hit the threshold of the person who's hearing impaired. But for a 60 dB sound, you need about 15 dB of gain for that probe signal to hit the threshold of the hearing impaired person. So once again, if you look at how much gain as a function of level you need in order to theoretically restore forward masking for someone with hearing loss, you end up with, once again, with this magical sort of 3-to-1 compression ratio that seems to come up over and over again when we look at what's needed in a hearing aid. And when you apply that to someone with hearing loss and do that forward masking paradigm, you see that you can restore forward masking to normal, but it depends on the time constant. Now, so if you have a very fast time constant where the gain can change very quickly, you can get the threshold of that probe tone back to normal because the gain is increasing quickly for the low level sound. But if you have very slow compression, you are preserving that poor temporal resolution. And so what we think of as temporal resolution could simply be as just the nonlinearity of the gain function, allowing for audibility of soft sounds that follow loud sounds. And so if you design your hearing aid right, you can restore forward masking and presumably traditional measures of temporal resolution. So it's not really a temporal resolution problem at all. This, of course, begs the question I mentioned earlier. There are some hearing aids on the market today that operate very slowly. What is the impact of that slow AGC on auditory function in the real world where we want to hear sounds in the gaps? For example, hear the fricatives of one talker in a gap of another talker. Is that being impacted? And so this, again, raises interesting questions that you can pursue psychophysically or with auditory models. I'll talk about one other measure here and then I'll conclude. So the converse of temporal resolution is frequency resolution, and frequency resolution is typically measured by having a masker at one frequency, and then you measure the detectability, the detection threshold of a probe signal at a different frequency. And you measure that at different frequencies and you end up with a tuning curve. So with normal hearing, if you had a masker, let's see, if you had did I get that wrong? Fixed level, yeah, the masker is fixed, yeah, at 4K. And then you measure the threshold of a probe at different frequencies. For normal hearing, you'll get a curve like this. As you get farther from 4K, you have an easier time hearing the tone and better at lower frequencies. And so that is a measure of the auditory filter in the person, essentially. Now, if you do that same task for someone with hearing loss, you see this very broad function. And the conclusion is people with hearing loss have much broader filters. And there's nothing you can do about that with the hearing aid. You can't narrow someone's auditory filter with the hearing aid. However, enter the benefit of multi-band nonlinearities. So if we look at the effect of two different compressor designs, one that has more broader filters and one that has a more of a narrow band filter, apply that as a front end to the psychophysical task with someone with hearing loss, and here's what you get. So again, in the dashed line, that's the normal tuning curve from a frequency masking paradigm. This is that unamplified hearing impaired data. And here are the results with two different compressor designs. This one with broad filters of an octave band, this with narrow band filters of a quarter band. And you can see it's starting to provide what looks like tuning in this paradigm. And what it really is, it's by having multiple bands, you can increase the audibility of off-frequency sounds that are at lower levels. So the gain at like 6 kilohertz isn't dominated by the input level at 4 kilohertz. By having multiple bands, you can have frequency selectivity in the gain that gets applied at a frequency. So I'm going to skip over loudness summation, which I mentioned earlier, but the short story is compression design can have a significant impact on whether loudness summation gets restored in people with hearing loss, because that is another phenomenon that gets affected. So I think just to summarize here, there are lots and lots and lots of perceptual consequences of losing compression in the auditory system. And the way I think about it is you want a hearing aid design that is going to restore the mechanics of hearing as measured by psychophysical tasks or as measured by auditory models back to normal as possible. Now, at the end of the day, it's still about perception, and you may, by your objective measures, it may be perfect and the person listens to it and it sounds terrible. So that's where the compromise in terms of having longer time constants and, you know, smoothing things and so on from an engineering perspective comes in. But from a theoretical perspective, I think this is a good framework of understanding what hearing aids should do based on our understanding of auditory function from primarily cochlear models, such as the CARFAC. That's it. Thank you.
Thanks so much, Brent. Really appreciate your perspective on all this.
Yeah.
You know, when I wrote this chapter, I spent a lot of time on sort of the older prehistory from people like John Allen, who's talked about AGC since about 1980, and Meade Killian, who built the K-amp chip, which is sort of a two-band compressor where one of the bands wasn't compressive, and kind of the first high fidelity hearing aids. And the idea is that if it doesn't sound good when a normal hearing person listens to it, it's how do you expect it to sound good when a hearing impaired person listens to it? Some of the simple advances like that, and you've built on a lot of that and got into a lot of the details. And in the in the CARFAC, I put in multi-time constant compression. So even though we call it fast acting compression, there's a slow acting component. And I think a lot of these things you see in the literature about fast versus slow really need to be investigated in terms of some of each. And
there are some hearing aids now that have this sort of dual time constant, sort of a slower AGC and a fast one that's working on top of that.
Yeah. I don't know how easy it is to actually get the evidence that that's an improvement, but it seems like it should be, right?
Yeah.
And you know, when we try to make the output as close as possible to normal of an aided impaired model, which is what we're doing in the hyper-personalization project, I think the key to getting several keys to getting that to work right. One is to have a good model of the impaired and normal system, but the other is to have a good way to compare them, because, you know, as you said, we don't there's a lot of cues, and we're trying to preserve different cues for different functions.
Yeah.
And some matter more than others. And so depending on what you measure in your comparison or in your loss function, in our case, you're going to get different results. So there's still a lot of open-ended questions in the whole thing. And we're hoping to have a structure in which we can do some more experimental explorations of that.
And that's why I think thinking about it from a perceptual cue perspective, you know, So you can just take a black box approach. We're just going to minimize the auditory nerve response from some error metric. But then if you do that, you say, well, okay, what is the resulting loudness growth curve produced? What has happened to the envelope representation? And you start to look at these different dimensions of what's important in auditory perception to understand what your system has done.
And those come into the engineering of the loss function. Is
Yep.
basically is where we need to work on them. So
Yep.
yeah, it's a framework, and we're not doing something that's completely different from what you've done for the last 25 years or 30 years or so, but it's closely related, obviously.
Yep. Yeah, absolutely. Julian?
Yeah, thanks very much for that talk. That was super interesting. I particularly found the concept of this Turing test for hearing fascinating. So, my understanding of that is if there's no test that distinguishes between someone with a hearing aid and without, then hey, the hearing aid's job is done, right? So my question is, like, where do you see we should be trying to raise the bar with these tests? Like, if we can, it's kind of this cat and mouse game. We want to make tougher Turing tests, and then we want to improve the hearing aid so they pass those tests. So are there some kind of real world Turing tests that are not yet being done that we should be aiming at trying to do?
So,
and also, is there any current test that no device passes?
Well, I think a lot of tests, most don't pass, but they nudge the person closer to normal. A series of research that we did in the mid 2000s at Starkey was basically taking Al Bregman's book on auditory scene analysis and looking at his basic measures of the auditory scene phenomenon, where you perceptually fill in the gaps, for example, where you stream or you don't stream, different tone sequences, and looked at the effect of different hearing aid designs on preserving those phenomenon, because that starts to get to the higher level representation to see are we screwing up the cues that's presenting the higher level systems from segmenting or streaming, different sound segments. And so with Dennis Baskent, who's now in the Netherlands, did a series of projects on that, and Sridhar as well, who has left us. Well, I think one thing that's quite important is localization and the impact of hearing aid processing on your ability to preserve the cues necessary to localize sound, so then you can use that very strong cue for source segregation. So we had a series of experiments on that as well, to look at different hearing aid designs on preserving localization cues. And we applied a model, might have been a Berger-Kohlmeier model, of how you figure out where a source is coming from given a broadband signal. So a long answer to your point, to your question, I talked about very fundamental psychoacoustic measures here. I think what's even more important are the ones that engage the whole auditory system in a way that's more natural of how we function in the real world. But for me, the bottom line is, what do people think? It's one thing to measure in the lab and prove mathematically and theoretically, but at the end of the day, if someone is functioning in the real world in a noisy environment and listening to music, and are they appreciating it as much as they used to? Are they functioning as well as they used to? That's the bottom line. And by the way, I do think music's a great signal to test the dynamics of your processing, because it's much more complicated and it's much easier to tell if you're screwing things up. Speech is so robust, you can really screw up speech and people will still understand. But music, you get that wrong with a music lover and they'll know right away.
Cool, thanks.
Yeah, I'd just like to add, Brent, I think that this Turing test, we've spoken about it many times, but one of the real points of pain, of course, is understanding speech in noisy environments. So one of the things to do would be to actually measure communication efficacy. What are the bits of information that are being transferred, and at the same time look at effort. I think they're the two key issues that the hearing impaired constantly bring up. Yeah,
agreed. Effort. We found some signal processing designs that had differences in effort, but no differences in other functional measures. So that's an important dimension. I've often thought that constant confusion is a great way at getting at how speech sounds are being encoded and looking at the differences in the confusion errors, consonant errors between normal hearing and the impaired and the compensated impaired. Abhinav?
Thank you. I had a question or a follow-up on the forward masking task.
Yeah.
I see that like one solution could be to adjust the gain, right? Where we can try to sort of get this probe sound to be louder. But the other part that I was curious about is the actual time delay. And
Yeah.
the motivation comes from this one experiment I read of from Popple Lab, where they actually get participants to sort of speak, kind of like, just repeat syllables in a rhythmic sense, and then they
Yeah.
stop, and then they give them an auditory probe. And then they show that the phase of the probe with respect to the sort of motor rhythm that they had going could actually impact their sensitivity to that auditory probe. So what makes me curious here is that, like, I see that, okay, we want to do a gain solution because it's probably murky to mess up with the phase or the timing of the signal. But has like a timing or retiming sort of approach been tried on the hearing side? Like if it's only a couple milliseconds of phase adjustment, would that be still like an alternative option than a gain solution?
Well, phase is something that has typically been ignored or used to be ignored in hearing aid design. I don't think it is anymore because of focus on localization. So is your phenomenon, is that more of a central effect that's happening? It's not a peripheral effect, is it?
No, because it's mostly engaging like a motor or some speech area in trying to decide when the auditory system is paying attention.
Yeah.
So it's definitely beyond
But
the periphery itself.
it points out the importance of considering phase in design as well, because it has, multiple impacts on perception and multimodal integration. One interesting problem is if you have high frequency loss, you're getting the unamplified sound coming in naturally in the open fitting, and then it's getting combined with the high frequency amplified sound that has been delayed by several milliseconds. And what is the consequence of that? I mean, yeah, think about that.
It's a mess. And if you're trying to do a task like detecting this probe tone after a steady masker, yeah, you can improve the performance by delaying that probe. That's what the curve shows. But you can't. That doesn't lead you to a strategy for processing sounds in general.
No, definitely not. That's a good point. David?
Such a wonderful presentation. Thank you so much. You mentioned consonant errors, and that reminded me of my idea of hearing test hell is that one where they give you the nonsense words and then ask you to repeat them.
Yep.
For those of you who haven't had that test, it's like going to a party in another country and being introduced to a bunch of people who have names that you've never heard before. It's really tough, and it makes me wonder about the fact that a lot of these tests people are exposed to them infrequently, every now and again. And the thing is, we have a capacity for improvement with practice. So, to add another complication to what is already phenomenally complex world, is there scope to look or explore at how people may adjust to hearing devices and sort of improve over time? Because I think if we're sort of like testing people and here you go, do this test, and just when they're getting the hang of it, it's like, thanks, bye, and off you go, that's a different scenario than you know, having a setup where someone might be deliberately practicing and adjusting and learning to compensate for some things. So it's not a very well-formed question, but I hope you get the gist of it, because it's about, you know, people's ability to adapt and whether it's possible at all to explore that in relation to compensating for hearing impairment.
Well, certainly people do adapt over time. We saw this in the linear world when we shifted from linear hearing aids to compression hearing aids, and people didn't like it because they had acclimated to really loud sounds over amplification, and they learned to like that. So it took them a couple of weeks for their system to learn that compression is actually doing things better for them. You know, learning to hear cues that you haven't heard in years. You know, when you bring back high frequency audibility is an issue. There's a little bit of adaptation to gain. You want to start someone with lower levels of gain till they get used to it, and then get back to what you think is a proper target. You mentioned the thing about names and learning names. There's an interesting study that was done that showed that just adding audibility, adding more gain from 6K to 10K, improved people's ability in a hearing aid, improved their ability to learn new words, which was, yeah. So better hearing means better learning. That was pretty amazing when it was first published.
Interesting. In the cochlear implant business, the adaptation to the signal is huge, because the signals are so unusual, your brain can't really interpret them as speech initially in many cases, and it adapts over a long time. And this makes it harder to try different algorithms, because each one needs such a long time to work around the slow adaptation of your brain to the signal.
Yeah, I used to talk a lot about things. Can't remember what the term is now, but when people first wear a hearing aid, one of their common complaints is, I can hear the refrigerator running. I don't like it. Or I can hear the air conditioner going and I don't like it. The thing is, all of us can hear that too, but we have adapted to ignore it. And they haven't had the time to learn to ignore it, so it's bothersome to them. And this brings in the question, if you got a system that's constantly changing gain and applying noise reduction and all this, will your higher up system learn to ignore the air conditioner? Is it constantly going to draw attention to itself because of the change detection that is wired to notice changes in sound? So that gets back to the dynamics, the time constants issue, you know, so it's complicated. Jinhu?
You're muted, Jinhui.
I'm sorry. So I was wondering, what's the typical number for the latency and window size and sampling rate for hearing aid?
Yeah, we discovered early on that you really need the latency to be below 8 milliseconds, or you actually notice an echo effect between the low frequency and the high frequencies. It's only when you get into tens of milliseconds that comb filtering becomes an issue, and then even longer, the foreign, you know, movie dubbing, asynchrony between the lips and the sound becomes an issue. So keeping it below 8 milliseconds kind of minimizes artifacts. And hearing is today probably vary between 4 and 7.
So typically that means like a 4 millisecond windowed input to your FFT and then overlap add.
Yep.
And that gives you 4+ milliseconds of latency.
Yep.
So the sampling rate is about 16K or 48K?
Usually
not 48, you know, it'll be, originally it was 16K, but now hearing aids go up to at least 10 kilohertz. I think probably 12 kilohertz now in terms of pass through. So sampling rate of at least 24 or, you know, or so. There's an interesting compressor design that Jim Cates created for Resound called a warp compressor, where he introduces a Z transform, a delay in between each sample, and it produces a time varying delay, even though it's an FFT. And so you get shorter delays at higher frequencies. which is an interesting approach. Again, you now have time varying phase, frequency varying time delay, which is unusual to think about, but
yeah, he did some studies to show that it was an improvement too, that even though there was some time delay, the fact that it was less at high frequencies was a benefit compared to that it's different at low frequencies. And to me, that's the smartest hearing aid architecture I've seen. And I asked him a while back if any hearing aids actually used that. He said, yeah, it's been in GN Resound aids for 20 years. So
yeah, but only Resound.
Yeah. Well, he was their employee or consultant or something for a long time, right?
He was at Audiologic in Colorado when Resound worked with Audiologic and Dynavox on our first programmable digital hearing aid. Jim developed our feedback canceller, which was incredible. Added 8 or 9 dB of added stable gain to our system, first in the hearing aid industry. When we merged with Dynalogic in '99, Jim Cates joined Resound signal processing team, which I led.
Mm-hmm. Yeah, I pointers to the list about that.
Yeah, and by the way, I tried to just drag a document into the chat here, but it looks like that feature is not available.
Yeah, I don't know.
Because I have that paper on the Turing test here. I was going to post. Maybe I can email it to everyone on the list if you would like.
Yeah, or even if you could post the reference, it'd be great.
Oh yeah, sure.
Look, I know time's running out. I just want to try and squeeze something in. We've talked about making adjustments to gain in different frequencies and so forth. What about approaches that actually shift the frequency of the signal? Like, I know it's going to change the nature of the sound. However, in certain situations there may be advantages. Has that ever been explored?
Yeah, most hearing aids have that now, and they do it in different ways. Because you're in the frequency domain of the FFT, it's really easy just to take your upper bins, pick them up, and drop them down in a lower frequency region, and some hearing aids do that. Others have taken the upper bins and squeezed them, interpolated the frequency bins to basically limit, basically squeeze it down. I developed a system that we introduced at Starkey where we created a pole model of the frame's frequency response, and then rotate the poles, around the circle, which basically shifted the peaks. So and then resynthesize the signal. The benefit of that is it preserved the fine structure of the signal, because you're only shifting the envelope in the frequency domain, but any fine structure is preserved. All the other approaches distorted the harmonic structure and produced artifacts, but by just shifting the poles, you preserve the harmonic structure throughout, but at the expense of a lot more computations.
Interesting. I know there's an Australian, Hugh McDermott, who did a lot of work on frequency lowering hearing aids. I never understood the approach very well because it seemed like it would distort the waveform way too much.
Yeah, the key insight from that came from Chris Turner at University of Iowa, showing that you have to limit who you apply this to, and it's the people who have really steeply sloping losses that will benefit from this. But if you have a moderately sloping hearing loss, there's no benefit to frequency lowering if you can provide that audibility. So it's about, figuring out who's the right patient for your solution.
Mm-hmm. Wow, amazing. Thank you.
Cool. Well, thank you so much, Brent. Sure enjoyed your lecture.
Oh, great. Well, thanks for the invitation. I enjoyed putting it together.